series is for what we will need the limit comparison. Yeah. So
See, is that 1 by 4 or 1 by 9?
sorry, that's 1 by 4. Yeah.
Okay, okay.
So just think about this for a bit.
Yeah. N power 4 plus 1 power 1 by 4 minus n. Okay. One minute. Goes to 0. Yeah. Zero. Zero. Whole thing goes to 0. Whole thing goes to 0. I don't know, sir.
Uh-huh.
I'm not getting it.
Yeah, so you see, in this case, because we don't know how to compare, right, this with any series.
Yeah,
So let's
yeah.
try to understand how this. So let's isolate the term. And okay, so my 4 is always like this. Let's try to understand what this expression looks like when n goes to infinity. Okay,
Okay.
what does an look like when n goes to infinity? So how do we usually do such a thing? Or let's say if I just ask you to
I
find the
mean,
limit of
n is going, like, I figure out that n goes towards 0.
it goes towards 0.
Yeah,
Yeah. Okay. Yeah, that's true. It does go towards 0, but we want a bit more information. We want at what rate exactly and so on. How did you figure out that it goes to 0? Maybe you can extend that technique.
yeah. So, you first, like, we'll rationalize this.
Uh huh. Okay. Okay. Rationalize
So,
it. But this is
like,
a
you,
yeah. Okay.
yeah. So, you can convert it into the form of root of n power 4 plus 1,
Root of.
power 1 by 2, yeah, power 1 by 2, minus n square
Mm-hmm.
divided by n power 4 plus 1, power 1 by 4 plus n. Now, see,
Okay.
as n goes towards infinity,
Mm-hmm.
the denominator goes towards infinity, and the numerator, like, you can ignore that plus 1 after a long time, it kind
Uh
of goes towards 0.
huh. Right. But
So 0 by infinity goes to 0.
that's huh. Okay. So that makes sense to me.
Okay.
However, that will like so we know that the terms go to 0. That's right. But
Huh.
we need to be able to say more than that, right? And let me tell you what I mean. So um, if I don't know if you rationalize this further, you can rationalize this further, but I don't know if that would help. So let's just try it, though I have a different technique in mind. So I'll say that if it doesn't work. So in that case, if you rationalize this further, this is what you're going to get, right? This and you're going to multiply this by the same thing. So let's just see, experiment it and see. This we will get like this,
Okay.
and this would become minus n to the power 4. Okay. So, okay, no, it will not be, okay, let's see. 1/4 plus n, and this is n4 plus square plus n square. So again, of course, we still know that it goes to 0. However,
Yep.
this is in this form, we can say much more. So
Okay.
firstly, we can just cancel the stuff that we can cancel, and this is 1.
And we can ignore the ones because after a long period of time.
Okay, yeah, we can ignore the 1 in this case because it's a plus sign also. Yeah.
Yeah.
So we can
Yeah.
ignore the 1. Okay. So if you ignore the 1, then the denominator looks roughly like, so at this point,
2n
maybe,
into
yes. Yeah. So it would look 2n yeah,
into uh, into n power 8 plus n square.
n power 8. Oh, no. So I'm sorry. This was not n, this was square root. I'm sorry. Yeah. So this becomes like n square, right?
Yeah. So 2n
2,
square.
2n square. Yeah. So this
Yeah.
is again roughly, I mean, it's actually equal to
Yeah.
n cube, 4n cube, right?
Yeah.
So this we say it is O times capital O times 1 by n cube, but that is not at all useful for us. Okay. So see
Yeah.
now
Now we
we
know that this one converges.
ah right, because it is similar. Even though we have not defined what similar b means in a very strict sense, we will define it and state the comparison test. But the technique is quite straightforward, right? You try to understand where the series is going, or what does it look like, which other series does
Yeah.
it look like when n becomes big. Just, of course, you said that it goes to 0. That's good, but that's not enough information. That's not telling at what rate. Now we know that it's
Yeah.
going at this rate. Okay.
Yeah.
So finally, let's just write it out because we're just doing it for the first time. So an, seeing this later, an is similar to 1 by n cube series
Yeah.
up to a constant. And so an converges, implies that an converges. So
So
you
what
see,
was your technique?
so well, it was quite similar. We would have applied the so I would have concluded this same thing. I would have arrived at this conclusion by using the binomial theorem without. So that is just escaping this two-step rationalization process. That's all. So
Okay, okay,
my solution would be algebraically simpler, but it would just give the same answer. But let's just
okay,
let me show you that also, because sometimes it can save a lot of time. So
okay.
we want to apply the binomial theorem. So I don't know if you remember this from if you've done this earlier. So something like this. So 1 plus x to the power r, where r could be any real number,
Okay.
and we want to be able to expand this. So we all know the binomial theorem when n is when r is a positive integer.
Yeah. Yeah.
Yeah. However, there is a version of it which works for all numbers, right? And of course, that can be proved and all that. But let me just state what it says. So, of course, for that, mod x has to be less than 1. That's the condition. And under this condition, you could write this as, and this is extremely useful. Okay. You could write this as rx, okay, r into r minus 1 by 2 times x square plus r into r minus 1 r minus 2 times 3 factorial x cube, and you can very well guess the next terms.
Okay.
Yeah,
Yeah.
it will just continue like this, and it will not be a finite series, right? Because r is not an integer, so this r minus 1 r minus 2, this will, it will just keep going, right? R minus 3, next one,
Yeah.
next time, next time r minus 4, it will just keep going. It's an infinite series, in fact. But since x
Okay.
is less than 1, the weightage of those terms will be very less, because when you raise
Okay.
the powers of x, it will, yeah.
Be very small. Yeah.
Yeah, right. So this is, and this
So
is,
1 plus Rx.
it is 1 plus, but it depends on how accurate you need to be. So it depends on how accurate you want to be, and we take that many terms as needed, okay? But just a few more words about this one. So this is very similar to the ordinary binomial theorem, right? Because even if it was the ordinary binomial theorem, it would be like this, right? N choose 2x square, n choose 3. Maybe you have used the different notation for n choose 2. So you must have
NC2. Yeah.
nc2, yeah, but it's the same thing, yeah. nc3
Okay.
x cube. Now, when you expand nc2, you get exactly this. Or when you expand rc2, right, you get exactly this. And in expand
Oh, so it's the same thing.
it is the same thing, but here we are making a much bigger claim actually, that this r can even be not an integer. And in that case, the nc2 doesn't make sense in the combinatorial sense, right?
Okay. Okay.
Yeah, but and the polynomial sense, it still makes sense. And so we extend that definition, and it in fact this works out. Okay.
Okay.
Okay, this is a very useful theorem. It's the binomial theorem for non-integer, non-positive integer, non-natural power. So how can we apply it in this case? So here we certainly see this is a candidate for applying the binomial theorem, because it's a very weird power on the top, and
Okay.
basically this is what it's doing, is converting this expression, which might have a very nasty power on the top, to an expression, or basically approximates it by an expression that does not have any strange powers on the top. Okay, because we
Okay.
don't like strange powers on the top. We don't understand them very well. But before we apply
Okay.
it, we need to ensure that this x is less than 1. So we need to make this less than 1 before we apply. And it's not less
So
than
let's
1.
take x power 4 common.
Yes, yeah, something like that, right? So you just take n power 4 common. You just take it out, right? So once you pull
Yeah,
it
so
out,
n will
it
come
just,
out. Yeah.
yes, right.
1 plus. Yeah.
Yeah. So can you just write out the first few terms using this expansion?
Yeah. So n stays out only. And
Mm-hmm.
then we are going to get 1 plus 1 by 4 in power 4
Mm-hmm.
plus 1 by 4 into 1 by 4 minus 1 into 1 in power 8 whole thing by 2.
Right.
Even more. Then again 1 by 4, 1 by 4 minus 1, 1 by 4 minus 2 into 1 by n power 12 whole thing divided by 6.
Right. So we can go on, but we need to understand how much we need to go.
How do we know that?
Yes. So let's see. So basically, here at this point, we have to see. Yeah. So let's see. So here, these terms, they are of a certain order, right? They are of the order 1 by n power 8.
Okay.
Yeah, because this is the most dominating term in this portion of the series that is infinite. It is
Okay.
infinite, but still the most dominating portion is 1 by n power 8,
Yeah.
right? So that is of that order. So we can just roughly write this as n times 1 plus 1 by 4 n power 4 plus, other terms are of the order 1 by n power 8. We will
Yeah.
see if we need to expand on that other part.
Okay.
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 Meanwhile, let's see if we can make sense of our expression using just this much approximation. If we can, then we don't need to go further.
Okay.
So our expression though is slightly different. So an then would be n times 1 by 4n power 4 plus order of 1 by n power 8
Minus 1.
minus 1. Yes,
Yeah.
absolutely.
So that 1 cuts. Yeah.
Uh, the 1 is, yeah, the 1 cuts, right? Yeah. And now you see this, now this expression makes complete sense to us, right? Because this becomes 4 by n cubed plus
Yeah.
other terms would become of order n power 7. Okay, is that right? Okay.
So when
Now,
you mean order n power 7 and 7 and more, you mean like that?
no, n power 7 and higher orders, I mean higher powers, but they
Okay.
will have less, but they will be less significant.
Okay. Okay.
You see my point, right? Yeah, so they'll be less significant. Yeah. So that's how you get it, right? So, how do I
1 by
say?
4 n cube. Okay.
Yeah, basically, then roughly the only term that matters is this 1 by 4 n cube, right?
4
Because
n
the other
cube.
terms are very less significant,
Yeah.
and that
Yeah.
clearly, this is maybe in some sense faster than the rationalization process, but this will also something that you get used to make it faster. Yeah.
Okay. Okay.
Okay. So yeah, but the analytic content of this thing is that, so eventually all this can be done in several ways, as we have seen 2 ways already. Eventually the thing is that we are showing, we showed in the end that this is roughly equal to 1 by n cubed. Okay.
Okay.
And so what does it mean actually? It means that n power 4 plus 1 to the power this minus this divided by 1 by n cube, the limit of this is 1.
Uh, yeah, because they're approximately similar. Yeah. Yeah.
Yes. Yeah. And but this is the formal meaning of that.
So
You see.
anything by anything, right? My wish, right?
Yeah, anything, no, but the first one has to be from the series itself, right?
Okay. Okay.
And the second
Okay.
one you have to decide wisely.
Okay.
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 In this case, the algebra and also helped us to decide. Okay.
Okay.
You
Okay.
could have also used your intuition maybe also, but it depends. But yeah,
Okay.
whatever we were able to decide. And then we basically concluded this. And actually one can now check this explicitly, that this limit is 1. That will be just a limit calculation. But anyways, we have also checked it.
Okay.
Okay, so and this is what we have, and then we know that this is converging, and hence this series, the series of the top must also converge. Again, that is something that we feel is correct. We don't have a proof of that. We don't even have an argument of that, right?
Okay.
Or yeah.
Yeah.
So let's try to understand the argument behind it. So maybe we
Okay.
can just do it on the side so that we can see the parallel. So let's say that there are two series. Okay, there is a1, a2, a3, this, and there is b1, b2, b3, dot, 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 dot. Yeah, and by the way,
Okay.
this was not 1, the limit was a constant. Yeah, it was a constant, 1 by 4, because it was, yeah, it was roughly equal to 1 by 4 times n cube. But yeah, the constant is not going to change anything. let's see. So say we have these two series, right? Now uh, if the AI is similar to BI, which means that limit AI by BI is equal to a constant as I tends to infinity. Okay,
Okay.
and yeah, so here I must be here I must say that C is not 0,
Okay.
and C is a real number but not 0. If it's 0,
Okay.
then we cannot say much. We'll see that. But if C is not
Okay.
0, then the claim is, and we have already observed, we already feel it's true, but the claim is that if sigma AI converges, right, then
Hmm.
sigma BI also converges.
And if it diverges, that also diverges.
Yes, right. That will also be true. So can we now? So this is something that we feel is correct, right? Because it means that AI and BI are similar series, and so this must happen. But can we give a more mathematical argument? So you can think about that.
More mathematical argument.
Yeah, because I mean we are saying this just based on our intuition, right?
Okay. Okay.
Mm-hmm.
Okay. 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 I'll tell you. Okay. 1 minute. Yeah.
Mm-hmm.
So why? Because see. So okay. I'll
Mm-hmm.
tell you. Suppose one converges and the other diverges. Okay. So
Okay.
when you see the other one diverges, means it goes towards infinity.
Mm-hmm.
Okay. So
Mm-hmm.
whether infinity comes in the numerator, then limit will become infinity. And if at all the infinity came in the denominator, then the limit will become zero. So for the limit
No,
to come a constant,
no. But see, the summation is may diverge, but the terms may still go to 0. See, we are sure that, so I mean even at the top we can make an assumption that AI go to 0 and BI go to 0. That we already
okay,
know.
okay,
Otherwise
okay,
they will not even be contenders for convergence. So the series is diverging but the terms are going to 0. You see,
okay, yeah,
yeah, that's the problem. So the terms are going to 0, and this is saying that they are going to 0 at the same rate. That's why the ratio is a constant and not 0.
okay, okay,
So this
okay,
is slightly more subtle, yeah, one
okay,
layer inside.
okay. Yeah,
Yeah. So can you think of something else that we can say in this? Like,
yeah. 1 minute. This
hmm
uh, mathematics. I don't know, sir. Nothing's clicking.
okay. Let's use the definition of this. Okay. So we are saying that AI and BI is similar, but what does that mean mathematically? It just means that AI by BI is roughly C, right? For all I bigger than some n naught. You can just take
Okay,
epsilon to be 1 in this case, right?
okay, okay,
It's roughly this.
okay,
Yeah, and for all n after a certain point, that may be very far, but it's there. So after a certain point,
okay.
AI by BI ratio is like this. Now you tell me, can you use this to, because this was a limit, I mean the series is similar, but now I've converted it into a purely, like a finite statement.
And what should I comment about? Like I should tell why.
So you should tell why. So you should tell that why BI converges if AI also converges. If AI
Okay,
converges. So assuming AI
okay.
converges, how do you conclude that BI also converges?
Assuming AI converges. Okay. Assuming AI converges. Okay.
Summation AI. Yeah.
Yeah, I get it. I get it. Yeah. Summation AI convergence. 1 minute. 1 minute. If AI converges, why BI also converges? So just one thing, when you mean summation AI converges, it's for sure that AI is not all positive, right?
Why? It can be all positive.
So if AI is all positive, then won't summation AI go to infinity?
No, that's why we are doing this chapter, right? Because that's the question. Sometimes it still is converging if it goes very slowly. For example, if AI was 1 by 2 to the power I. Mm-hmm.
Okay, okay.
Mm.
Okay. Sorry, yeah. Well, I don't know, sir. What?
Okay. So see, if summation AI converges, basically it is saying that it is bounded. Yeah.
Yeah.
Yes.
So one more thing, sir, hold on. If summation AI converges,
Mm-hmm.
that means that limit n tends to infinity, an is 0.
Yeah, that is true. That is true. But that doesn't say anything, right? Because
No, not that, sir.
mm-hmm.
Okay, yeah, that doesn't say anything.
That doesn't say, that's very weak statement. That just says that okay, then limit of bi should also be 0, because otherwise the ratio will not be a constant. But then yeah, okay, limit bi is 0, but that doesn't say anything.
Okay.
Yeah, so see, I mean, basically it's just a matter of boundedness. I mean, we are doing this for the case when all the terms are positive, and I think it only holds when all the terms are positive. Or does it hold for other cases? Let's just assume that, yeah, I think it does hold for when the terms are not positive as well. Let me just think 1 sec. No, it will not. So all the terms have to be positive for this one. Okay, that's the blanket assumption. But that's fine,
Okay.
because I mean, yet we are just doing positive series only. So yeah, that has been the assumption. So basically, it's just a matter that the matter is that the summation AI is bounded. It's bounded above, right? There is some number m. So that symbol basically means there's some number m such that this is less than m. Right?
Okay.
Meaning that all the partial sums are less than m, and even after adding, and the limit of that is also less than equal to m. We can actually just say it is equal to m. Okay.
Okay.
All right. Now, if you think about this, so now how do you show that bi also is less than some m? It doesn't have to be the same m, right? It may be a different one, but just show that it is also less than some m. So just put bi on the lesser hand side, because that's what we're trying to do. That's it.
Okay.
So once you, and well, here you can assume the c is bigger than 1. If c is lesser than 1, then the inequality will switch, and we can use the other side. But that's fine. That aside, this right now, if this happens, then you can just sum this inequalities up, right?
Okay, yeah.
And that's it. This is m by c minus 1, and so the summation bi also better be bounded, because it's positive term. So bounded means convergent.
Well, how did you split sigma as a product?
Wait, no, where's the product? Not a product. It's a summation. This means, where is the product?
No, not that, sir. Sigma AI divided by c minus 1. How did you write it as sigma AI by sigma c? Oh, c minus 1 is a constant.
Yes, there's a constant. That's a good thing, right? It's a constant.
Okay.
That's the most important thing.
Okay.
So you see, this is a very important test, and you can do it the other way also. Okay, I'm not going into the detail of that. In either ways, we don't need a proof, right? But
Okay.
yeah, but the idea is that you divide the series, and you divide both the series. So basically, see, if AI is a series that you are given and you want to check if it's convergent or not, and if you can think of a series that comes close to it, then you divide by that series and check, right? If the
And if
divide,
it is a constant,
yeah,
and then if one of them converges, the other also
others
converges.
also converges, yeah. But the key is to guess what other series you should be taking, right? For example, in this
You should
one,
manipulate the nth term of the given series.
so you would have a formula for that and you manipulate it, and then you see like this one we basically manipulated the nth term. That's all we did, right? And then
Yeah.
we guessed that it is almost like so. Then we compared
Yeah.
it. We told that we should compare it with
So
this.
one more thing, if the limit comes 0,
No, so you see, yeah, if the limit comes 0, so I'll ask that question to you. What happens when the limit comes? Then what all can you say?
the
So let's say,
limit comes 0. Um, yeah, if the limit comes 0, it's possible that the bth term, bi,
mm-hmm.
goes to, it's possible that bi goes to infinity.
Yeah, you
Now,
see,
if
right?
bi itself goes to infinity, then sigma bi diverges.
Yeah,
Whereas AI can be,
convergent.
uh,
Yeah.
AI can be convergent. Yeah.
Yes, right. So this basically says that the rates are not same. AI and
Huh, huh.
BI, even if BI doesn't go to 0, then there's no question. But even if it does go to 0, even then the rates may not be same, right? For
Hmm.
example, if you take AI equal to the 1 by n cube series and BI equal to 1 by n square series, right? Then AI by BI would be 0, right? It would be 1 by n,
Hmm.
and that would be 0. So it means that from the convergence of summation 1 by n cubed, you can't comment anything on the convergence of 1 by n square.
Square.
Even though 1
Yeah.
by n square is converging, we have proved that, but we can't comment
Yeah.
it from here. Basically, you can't
Okay.
compare a series which converges much faster. You can't use that to test the convergence of a series which has a bigger summation and takes a longer time to become small and
Yeah.
such.
Yeah.
Yeah, that's what it is. So this is the comparison
The,
test. Yeah.
the same thing for limit goes to infinity, right?
Yes, yeah. If the limit goes to infinity, then also, right? Then, I mean, if the limit goes to infinity, then you can obviously say that BI should also converge, right? Yeah. So let's look at this case separately. Yeah. So try to think about this a bit.
If it goes to infinity, one of the possibilities is that A1 goes to infinity. Means A1 diverges.
But that cannot happen because we know that
And
summation
B1
an
and B
no. But summation AI is converging, so AI is obviously going to 0.
why, sir?
No, because this is in the hypothesis, right? If
Oh, okay.
summation,
You told it converges. Okay, okay.
yeah, I'm saying that if we have this hypothesis, then can we conclude the second one? That's the question, right? Yeah.
It's not possible for the limit to go to infinity, right? Like if sigma AI converges,
Mm-hmm.
okay. So see, limit that means limit AI I tends to infinity is 0, definitely.
Right.
Now 0 by what limit will give infinity? Nothing.
No, it can. So if there is something else which goes to 0, but at a much faster rate, then comparatively AI might be a bigger series or drastically bigger series. And once again, you can just take example like this, right? So you can take,
So you're telling a 0 by 0 limit can become infinity.
yes, yes, right? Because just think about it, like
Okay.
take two
Wow.
series which both go, take two sequences which both go to zero, but they go to zero at very different rates. For example, I mean, you can take, um, yeah, you can just take this 1 by n and you can take I mean, 1 an. So you can take an as 1 by n and you can take bn as 1 by 2 to the power n. So what do you think will happen?
I mean, Bn decreases at a much more
Faster
faster
rate,
rate.
right? Both are going to zero, but now, so clearly, if you take the ratio, this would be 2 to the power n by n, which is infinite. And that's
Okay.
what this convergence of series is all about. It's not just about whether something goes to zero or not. That has to happen. All of these guys have to go to. If they don't, then we just don't even
Okay.
think about them. The question is at what rate?
Yeah.
That's why we are comparing them.
Okay.
Yeah. So this is
Okay.
possible,
Okay.
but this problem is really this version is very actually easy in the sense that think if AI is converging and AI is much bigger than BI. This is what basically is saying, right? That after a certain point, AI is much bigger than BI. And if AI is much bigger than BI and summation AI converges, then summation BI
Then the
must converge,
smaller one has to definitely
has to
converge.
converge, right? Yeah. Now this is a matter of writing, just a matter of writing it out. It
Yeah.
means that this is
Right.
bigger than M, right? So I mean, you take this. What does limit being infinite means? It means that it becomes arbitrarily big. It means that you take
Yeah.
any M and it would become, the ratio would become bigger than M after a certain point,
Yeah.
I bigger than n naught. And that basically now it's clear, right? Because just like this, right? And if this converges, then this obviously has to also converge,
Okay.
right?
Yeah.
So this is actually like a very much easier case than the constant one. Okay,
Minus infinity won't come since we're all taking positive
we are
terms.
all taking positive terms. So
Yeah.
let's also see why I said to take pop, because even I was confused just for a second, and even we can check if I was wrong. Let's see. So the problem if you don't take a positive series is the following. Let's say you take the um okay, so let me see. I might be wrong. Might be wrong in this. So hmm just one second. Yeah, let's see. So let's take this series. So you take AI equal to 1 by n. Okay, I'm sorry, I'm always making this mistake with the indexing. So an equal to 1 by n. And you
Hmm?
take bn to be minus 1 to the power n by n. Okay.
Okay.
Now you look at the ratios. So the ratio is a constant, right? The ratio is just minus 1.
Yeah.
Oh, wait. Am I getting it wrong?
And,
Oh, no, it's not minus 1. It's either minus 1 or plus 1.
plus one. Yeah.
Yeah, so the ratio is that this case is a little complicated, yeah, but the biggest possible ratio is still 1, right? So this is less than 1. Yeah, this is
Okay.
less than 1, but even then you know that summation an diverges, right? But we will show after some
Yeah.
time that summation bn in fact converges. This is not a trivial statement. This we'll have to check. Okay.
Okay.
Yeah, yeah, see I'm just trying to say that this we have to be careful about this test when the series is we have to be careful about this test if the terms are not all positive. Okay,
Okay. Okay.
so yeah, that's all I'm just trying to say. Though even at this point I'm not 100% sure if this will not, I think this theorem may still work, so let's just think a bit. So okay, let's just do it. So let's not make any, because here also the example I've given is not perfectly good, right? Because this limit is oscillating itself. So
Yeah.
just give me 1 second. So if this condition is given, then how do we break it down? It just means that this less than c plus 1 and this is bigger than c minus 1. Okay. Yeah, but the problem with this is that I mean you you can't really send the BI to any side, right? Because you don't know if the BIs are going to be
Yeah,
positive
because
or
you
not.
can't, you don't know. Yeah.
Yeah,
Yeah.
that's why I'm not very confident about this test in that case. And either ways,
You
this
should
test
take
is.
cases maybe.
But the problem is that some terms may be positive, some terms may be negative. What are you going to do?
Oh.
That is a problem. Yeah, that is the yes. Yeah, that is a problem, right? And even if you do end up showing that summation AI is less than summation BI, let's say something like this, or vice versa, even then you can't conclude anything because this may be bounded and this may also be bounded. Okay, both may be bounded by M1 and M2, but that is not
Ah.
sufficient for it to converge because the terms are not positive. Okay, so essentially the problem is, the point is that we don't
Okay.
even
Okay.
understand the convergence when the terms are not all positive. So once you have to understand that first, in the later section, then only we can say. But yeah, it will not hold because as you can understand, we can't even take it upside and so on. Okay, so yes, yeah. But
Yes.
anyway, this is stated only for positive series, so we don't even have to worry about it. Yeah. Okay, so let's try to use this test though in a few places. That's where the real
Okay.
usage of it is.
So the thing is, we should figure out the BI ourselves.
Yes, but sometimes you can take help of algebra. You can take just use your intuition. Yeah, but
Okay.
yeah, they will probably not tell you. Okay, if they do tell you, then it's easy. Yeah,
Okay.
then probably taking this limit would be hard.
Okay.
Yeah, so I don't know. Okay, let's try a problem. So here we have this half square root of 2 by 3 and 3 by 4 and so on. Yeah, you understand the pattern. So now the question is again, is this convergent or not?
Converging amount. So to apply ratio test, what is the only condition? Nothing. It should be
Ratio test.
positive. That's it.
No, this is not the ratio test. This is a comparison test.
I mean, yeah, this limit comparison test.
Yeah, only positive. There's no like increasing or decreasing condition.
Okay. Okay. So yeah. Let me just think 1 minute. So just telling, as n goes, see the nth term
Yeah.
is under root n by n plus 1.
Mm-hmm.
Okay. So just saying if n goes to infinity,
Mm-hmm.
an goes to 1. Okay.
Yeah.
If an goes to 1, the series definitely goes to infinity.
Yeah. So this is like a very trivial question in that sense, right? So you're basically just comparing it with the series bn equal to 1.
Oh, it's
I
called
mean,
like that. Okay. Okay.
if one has to and I say it and that, but yeah, it's obviously divergent.
Yeah. Yeah.
So let's move to the next one. So here we have 4 by 1, 6 by 9, 7 by 16, and so on.
So an is nothing but n plus 3 by n square. Okay. Okay. So this looks like as n goes to infinity. Okay, so I got an idea. Yeah.
Uh-huh.
So the nth term here is n plus 3 divided by n square.
Mm-hmm.
Okay. So we'll manipulate it and write it as 1 plus 3 by n
Mm-hmm.
whole thing divided by n.
Right.
Okay. Now, if this goes infinity, you can ignore the 3 by n. So it
Mm-hmm.
looks like 1 by n.
Right. And so if they
Bi
ask
is
you
1 by n.
exactly, yeah, bn is n by
Yeah.
n. If
Yeah.
you formally write, you should just say that. But you see,
Yeah.
we knew it from there. that it is like
Yeah.
that. So
Now we can do limit. So
yeah, please say. Yeah.
now limit n tends to infinity. We can take the limit.
Yes. A n by b n,
So
you
that's
mean?
yeah, an by bn. So it has to be, if you do bn by an, it gets messed up.
It will still be the same. You might
Okay,
look difficult to calculate, but it will be the same answer.
okay. But the answer comes out to be 1.
Hmm.
Yeah.
So it means that if one diverges, then the other also diverges.
Yeah,
Right?
correct.
And one of them does diverge. So the other has to
Yeah,
diverge.
yeah.
Nice.
Got
So this was actually an example we did earlier.
it.
So
Okay.
yeah, now let us do some example which we did not do. Yeah, so let's do this one. This is a very interesting series. This is one.
So the above test is called limit comparison test.
Yeah, that's what they call it. Yeah, it's not the ratio test because
Okay, okay,
really we are taking an help of an external series. So it's more like a comparison.
okay,
Yeah, but it is a more sophisticated kind of comparison because if you think about it, what was the limit comparison is basically like comparing a series an with a b series bn,
correct, correct.
right? But ignoring the first finitely many terms.
Okay,
They're
okay,
saying that if something goes
okay,
wrong with the first finitely many terms, it's not a problem. Eventually, if things
okay,
are okay, then we can just do it, right?
okay,
That's why, and computing the limit, it's easy. We have techniques for that. That's why limit comparison test. But the
okay.
problem with limit comparison is that it is still using an external series.
Yeah, yeah.
Yeah, but the ratio test kind of internalizes that thing and just compares the series with its terms with themselves. So this is much
Okay, okay,
easier. Okay, but we
okay,
lose something in the process as well, but we'll see.
okay,
Yeah, so but
okay.
it's much easier for a lot of it works.
In
It helps us to conclude for a lot of cases. So
okay, got it.
yeah, let's do this. Convergent.
So this is 1 by root n.
No.
The first thing I would like to tell you is that if there was no restriction, then I could have used the integral test here, number 1.
No, but this is not square root. So this is a very old notation of the factorial.
Oh, it's factorial. Okay, okay,
Yeah.
okay.
Nowadays they say they don't use this. They use the exclamation mark. Right?
Oh, we can't integrate a fact. So is there integration of x factorial?
Integration of x factorial. Yes, but for that you have to define x factorial as a function on the reals. So right now n factorial is a function on natural numbers, right?
Yeah,
So
yeah,
if you want to talk about it, if you wanted to talk about integrability of this thing, then you have to extend this function, right? And define
yeah.
it for all input for all reals. But if I tell you 2.5 factorial, what are you going to do with that?
It
You
does
don't
not
know.
exist, right?
Yeah, I mean, actually, we can define it. There is a way to do that. That's called
Okay,
the gamma function. So
okay, okay,
we define some function gamma of x, okay, some by some integral, and we show that this function, when integer values are put in, then it behaves exactly like the n factorial will know, right? And so we call this the
okay,
generalization of n factorial, and then you can integrate and
okay,
all because then it becomes a continuous
okay,
entity. But we
okay,
don't need to do all that. Yeah.
okay. So an is 1 by n factorial. Okay. It looks like what I'm thinking. It looks like 1. So any hint?
I think you can just use simple comparison also.
Acha.
Hmm.
Okay, okay. 1 by 2, 1 by 3 into 2, 1 by 4 into 3 into 2. If you compare with 1 by 2, 1 by 3, 1 by 4. Okay, we know that the basic harmonic series, can we compare it with, yeah, the basic harmonic series diverges.
Yeah.
No, but this is a term smaller than that. No,
Yeah. So we can't really use this.
yeah, wait, wait. Or we can take 1 by 4, 1 by 9. So consider the P, consider 1 by n square, okay? Sigma 1 by n square. Now sigma 1 by n square converges.
Right, yeah.
Wait, if this converges, so a smaller one definitely converges.
Yes. Yes.
So this is smaller than that, right?
Yes, of course, right. That's right. This is smaller because it's smaller because this is like you're multiplying from 1 up to 4.
Yeah,
Right.
yeah.
And here you're just multiplying 4 with itself and so on. Right. Maybe
Yeah.
maybe the first few terms are exceptions. Like this is not true. In the first few terms, it's not true because 1 by 2 is bigger than 1 by 2 square. But after some terms, it is
Okay.
true. You see my point, right? Yeah.
Okay.
Yeah,
Yeah.
that's the thing.
So what's the other way?
This is so basically see basically this is comparison test is giving the answer, okay, but
Okay.
you can just do it like this also. You can just say that I will compare 1 by n factorial by 1 by n square series. 1 by n square series is the canonical choice, I agree. Okay,
Okay.
so you just take it and do it. Okay, but this is very easy, right? Itself they have given it, so I'm just
No,
doing
sir,
it.
but what is the limit?
Yeah, but you see the limit will in fact be, yeah, so you tell me what the limit will be.
Infinity by way bigger. Limit is 0.
The limit is 0, right? And that's not a problem for us, right?
That is a problem, right?
It's a problem. Okay.
I mean, if it is 0, we cannot comment, right?
No, we said, right, so we cannot comment, but now you just think on intuition that there the hypothesis was different. In this case, the denominator wala thing is converging, right? And the numerator is much smaller than that. That's what limit
Okay.
0 means. So it must converge.
Okay.
You see, right?
Okay.
So basically, in that problem, the top one we took as converging. So we should have taken the top one here as 1 by n square. Bottom one is 1 by n factorial. Then this would come out to be infinity. And we observed there that if this is a case and the top one is converging and the bottom one is much smaller than that, because the ratio is infinite, so that must also
Okay.
converge, right? But you see, it's better to just just think on intuition
Yeah.
and compare it.
Okay.
Right. So yeah, this is easy. In fact, this is probably the most useful series in mathematics. This is like this is E. You must have seen this. Maybe this is the expansion of E.
Okay. Okay.
Yeah. So yes. So and we all know that E converges, right? So yeah.
Oh.
Because E is a number. E is 2.7 something. We have even calculated its values. 2.7 something. Yeah.
Yeah, but 2.7 some. Yeah. Okay. Okay. Yeah.
It's an approximation in the end of the day because even when I said that is pi square by 6 some series, we don't even know what pi is. Pi is only an approximation. It's
Yeah.
not a
Yeah. Got
number
it.
that we can precisely understand.
Yeah.
So that is the thing. Now let's take a little but this series was still quite easy, right? It was obviously convergent
Yeah.
because it was very less than n squared. That's why the ratio was
Yeah.
0. Let's take a
Yeah.
series which is slightly more interesting. So this is like products, two products. So 3, 4, 5, and so on. So
Okay.
think about
Alright.
this question is this one.
So En is 1 by n into n plus 1 into n plus 2. Okay. So, okay. One into n plus 1 into n plus 2. Okay. So can I just randomly compare it with 1 by n, like randomly?
You can try, yeah, because it has to be some trial and error. Yeah.
So like if I take Bn as 1 by n, and if I divide it, I'm going to get the limit as 0.
Yeah, but then we can't say
Limit
anything.
is Okay, you can't see.
because because when you just think about it intuitively, it means that bn diverges, summation bn diverges, and an is less than that. That's what this ratio is saying. But then okay, but so what? We can't say anything
Yeah.
from there. Yeah. So 1 by
Okay.
n is not a good choice. That's the thing.
Let me think 1 minute. Sir. No, sir. What somehow clicks in my mind is I
Hmm.
forgot about it, but there's a technique to convert this product into sum or
Into
something.
yeah, right. That's a much more harder question. In fact, this is an easier question. There
Okay, okay,
you will actually end up summing the series. You'll actually end up getting the answer.
okay, okay,
Okay. It can be done. So I mean, you can do partial fractions. Right? That's what it is, right?
okay, okay.
Um, if I
What
remember,
should I keep at the end? Uh, what if I take 1 by n cube?
yes, exactly. That is what it is, right? 1 by n cube is the way to go because this is like n cube only, more or less.
Yeah, I get it. So the limit will come 1.
Yeah, yes, right, and it will come one, and so you're done. Because you know that 1 by n cube
And
converges.
yeah, got it. Sir. Yeah.
Yeah. So see, this is much easier than you would if you would actually like try to do, because yeah, as you said, it can be done. So you have to do some kind of partial fractions, and then it will become a telescoping, like it will terms will cancel out, right? You write like this,
Mhm.
and if sum it, the terms will cancel out diagonally, whatever. You'll actually end up summing the series, but we don't need to do that. You'll be just
Okay.
asked to comment. That's the thing about this chapter, right? We are concluding that things converge or not without actually finding the limits.
Yeah. Yeah.
Yes, so that was easy. Let's do this
Yeah.
one. So this one is one of the questions we did a bit earlier.
Okay.
Minus n to the power 4 minus 1. Yes. Let's
Okay.
see. So again, the limit is like this, and
Okay. So if I rationalize this is a square minus b square. So n4 is gone, and 2 divided by root n4 plus 1 plus root n4 minus 1. Now, okay, and 1 minute, huh?
hmm.
Okay, suppose I'm taking my bn as n square, okay, 1 by n square.
Hmm. Yeah.
So 2n square by this. So the limit will turn out to be 1.
It won't be 1, but it will be a constant. It will be 2, I think, or 2, or maybe it will be 1. Maybe you're right.
Yeah, 2 by 2 will come.
2 by 2, right. So it will be 1, in fact. Yeah. So you see, it's done. So now you now you have
Yeah.
got the knack of it. Like what?
Hang of it. Yeah, yeah.
Yeah, that's what. Yeah, right. So this is really a very important test because here we could
So
not use the
basically,
direct.
for
Mhm.
you can use any test you want, like
Yes, you can use a lot of tests for some problem, but for this kind of problem, integral test will not try to think of it, right? Though it will also work. You can still integrate, but the integral will be difficult.
difficult. Yeah,
So yes, if you can do it, basically the idea is to do it in the fastest way possible. Yeah, the
yeah,
best test that is there for that.
yeah,
I mean, see, in this one, you could have also just used comparison, right? Because this is bigger than n square, and this is, yeah, but you cannot use direct comparison because this is not bigger than n squared. So you can say this is bigger
yeah,
than n square minus half. That you can say, right? And the sum is like this, and so 1 by that is less than 1 by 2 n square minus half. So you can use a
yeah,
sophisticated kind of comparison also, but with the limit, it takes care of this, half and so on, something like
yeah,
that. Yeah,
yeah,
that becomes easier. So
yeah,
anyways, yeah, so all the tests are quite related, right? We started with the comparison, then we started with, the limit is 0, then the series does not, if the limit converges, then if the series converges, then the limit of the nth terms has to be 0. When it
0.
is not
Yeah,
0, the harmonic is an example of that. Then we took the
Yeah.
technique of that and we abstracted the technique. We went to condensation, from there we went to integral, and it's all very connected, right?
Yeah. Yeah.
Yeah, I think it's good to see it like that. Yeah, better to not see it just like a sequence of tests come one
Yeah.
after the other, right? So let's see.
Yeah.
So now we have this one. So is this convergent?
Sine 1 by n.
Summation, yeah, sine 1 by n, summation of that.
Okay. Okay, 1 minute. Okay, so you compare it with 1 by n, okay?
Compare it with
So
1 by n.
basically sine 1 by 1 by n, and you take limit n tends to infinity, answer will come 1.
Ah, nice. Right, and then?
Yeah, so we know 1 by n, right?
Yeah, we
See,
know.
if 1 by n diverges, so sine 1 by n diverges.
Yes, very nice. And see, this would not be, yeah, this is a good one, right? Yeah, I mean, in the sense that you could have also used the following. Basically, you can also use this one, this inequality. So I don't know if you remember. This is another one, right? Sin x is always less than x.
X, yeah.
That one. So you could use
And
that,
tan x
and
is always greater than x.
yeah, at least between 0 and pi by 2, both are true. So
Okay.
you could have just used a direct comparison also. Oh, no.
Okay.
Sorry, what am I even saying? I'm sorry, no. This is true, but then this would not be useful, right? This diverges, but so what?
Smaller than, yeah.
We can't say, right? But this limit being 1 is a much more profound statement, right? This basically says that sine 1 by n is almost same as 1 by n, right? And that is because this limit, we know that sine x by x is 1. And this needs some proving to do. This is not a trivial statement, right? We always assume this one when x goes to 0. But yeah, with that assumption, it becomes easier. So we are using our limits also in this limit comparison test, knowledge of limits.
Yeah.
Let's do this one. What about this one? Sine inverse 1 by n.
Sine inverse 1 by n, okay. The same thing, so it'll still come 1.
Right, yeah. So same thing. But in this one, you can use direct comparison, because sine inverse 1 by n will be bigger than 1. Wait.
Yeah.
No.
Bigger than 1 by n.
Is it bigger than 1 by n? Yeah, right? And so you can just use a direct comparison in this case. Yeah.
Okay.
Yes. So let's go to the next one. Yeah, so we are almost done with all this. Now, what's next?
So we have ratio test, root test, and all, right?
Yeah. We have that. So now basically that's where we are. Yeah. So now we come to the ratio test. So now we are left with the ratio test. But see, these sections are very small in your notes. Okay. They just have defined it and given one example. They've not given any exercises on them. So there is a ratio test, root test. Then there is Rabi's test. I don't even think they will ever ask this, but I don't know. They can ask. And then there is a Gauss test.
So the absolute Leibniz.
Yeah, the Leibniz, those were important. Yeah, those come later. Yeah, so there's absolute and conditional. So there's
alternating series.
Yeah, in conditional, basically the alternating thing comes. Yeah.
Okay.
So this is all that's left. Yeah.
Okay.
These topics are very small here, so we'll just do them. Let's do let's start with the ratio test. Okay. So let's see what it is. So here is the ratio test. Right. So how can I start with an example? So suppose basically the core of this is comparison with geometric series. Okay. Comparison with geometric. Very simple idea with geometric series. So for example, I mean, if you have something like 1 by n, x to the power n, or maybe 1 by n half to the power n. Okay, and then summation of this would clearly converge, right? Because 1 by n half to the power n is less than half to the power n. Isn't it? Yeah, so this is something that we know. However, if you had well, one second, let me think. So yeah, however, if you had something like this 1 by n plus 1, okay, or maybe something more complicated like square root of this. Okay,
Okay.
if it was just like this, maybe you can just split it up and do something, but let's say we put a square root on top of it. Now you cannot compare this directly. You cannot
Okay.
compare this directly with half to the power n, because this is bigger than half to the power n,
Yeah.
right? So direct comparison with half to the power n doesn't work. How? So
Okay.
yeah, so I'll just write it here. Direct comparison fails,
Yeah.
or direct term by term comparison fails. And even group and
Okay.
comparing doesn't look very hopeful here because of the square root.
Yeah.
But yeah, let's see. So let's try. But even if someone gives you this question and you want to test whether it will converge or not, what are you going to do? You're going to just try it. Maybe you're going to try to take its ratio with the you could try to take its ratio
With
with half to the power n series, right? So
yeah.
if you're going to call this an, then that's your best bet, right? That you take half to the power n series and you compare it with that, right? So if you
Yeah, the
compare it with,
ratio will come 1.
absolutely, yeah, the ratio will come 1.
Yeah.
And so you see, with the limit comparison, you are able to say it. Okay.
Yeah.
It basically means that in the end, it just becomes like half to the power n. Okay. But direct comparison doesn't
Yeah.
work.
Yeah.
Okay. Right.
Yeah.
Now let's see. I mean, you could have used a direct comparison also, but you have to guess a better value than half. Maybe this is less than 2 by 3 to the power n that you can show.
Okay. Okay.
Okay, yeah. So it's something like that. So if you just be a bit creative, if you do not want to use the limits, like suppose if you're doing this teaching to someone who doesn't know limits, and then he'll try to
Okay.
guess something like this. Yeah. So
So half power n is a what series?
half power in a geometric, right? So that is just a geometric series, right? It is,
Okay. Okay. Okay.
yeah,
Okay.
it is
Yeah.
just
Got
a simple geometric series. Right. So now let us make this question even more harder and see. What if we had something like n times half power n? So I'll let you think about this for a bit. Yeah. What would happen? Then
Yeah.
we'll
Now, but
discover.
now if I take the limit, it will come
Hmm.
infinity.
Yeah, yeah. So now limit comparison fails in this. So that's why I'm just trying to discover the ratio, like just show why it's important. Why not just stick with limit comparison?
Mhm. 1 minute. So, but what if I okay? I mean, what if I take my no 1 by 2? No, it won't work. It won't work.
Yeah. So I mean, if you're going to compare it or even do limit comparison with half to the power n, it won't work.
Won't help. Yeah.
Yeah. So then what should we do? Yeah. So the thing is that this n. Wait. What am I saying? Once again. Yeah. The thing is that this n is going to make the series, making the series bigger. But even
Yeah.
then, you can find something. You can find an exponential series such that n is dominated by that. So what I mean is,
Okay.
you can find a very small series, like actually, no matter how small you take, you take, you just take 1 point. I'm just trying to emphasize the point that you can take it very small. Even if you take this is true, right? After a certain point, after some point,
Yeah.
because
Yeah.
exponential
Yeah.
series will eventually, of course, even in the first 1,000 terms, maybe this is not true,
Yeah. I get it. So yeah.
but yeah,
Yeah.
eventually this will be true, right? So then,
Yeah.
and I've chosen this to be, very. Oh, wait. I have chosen this to be very small, but the problem, yeah, that's fine. I'm sorry. This will work. Let's see. So now if you multiply this with half to the power n, then this becomes less than this, right? Now look, this quantity 1.001 times half is less than 1. Yeah, this quantity is less
Yeah.
than 1, right? It is around 0.5
Power
something, right?
n, it will come towards 0. Yeah.
Yes, right. So the ratio is, yeah. So now you see we are successful in finding an r. In this case, r is equal to not half, but a little bigger than half,
Okay.
such that, yeah. So you see now we actually ended up setting up a comparison test. I mean, this will not hold initially; it will hold eventually, right? Because
Okay.
this does
Yeah.
not hold events. So it's like more like a limit comparison. But even then, it's so straightforward that we can just say that after n equal to something, you will hold. You don't even need to use the word
Yeah.
limit. So this is like something that doesn't need doesn't need calculus, just needs some intuition about numbers, right? So there you go. This is the done. So we were able to do this question, only that we had to find a different value of r. We had to come up with a different value of r smartly. But the problem is that if your function is complicated, then you may not always be able to come up with it, right? So yeah, so here is the thing then. Here is the abstraction. Coming up, we don't
So one
always,
thing, geometric series always converges, right?
yeah, for r less than 1. Yeah,
Okay. Okay.
right? So here is the thing. We do not always want to do the work of coming up with a series like this. Coming up with a series,
Okay.
sorry, coming up with an r, right?
Okay.
So we instead compare this with the property. So let's see. So if summation an is a series such that there is some r such that an is less than r to the power n. Okay, so let's say summation an is a series that you started with and whose
Okay.
convergence you're trying to guess. And let's say it looks a bit like this, though it may be more complicated, right? It could be n cube plus 1 by n squared, blah blah, like some very
Yeah.
complicated thing. Okay, but the point is that it has some x to the power n to it. Then if you know that at the end of the day, if you know that there is an r for which an can be made less than r to the power n, then your job is done,
Okay.
right? Right, because
Yeah.
I mean, for r less than 1, right?
Yeah.
But we want to, but how do you decide this? How to
That
decide,
R. Yeah.
yeah, how to decide that r is the problem? So
Yeah.
even if you can't decide the r, because r is this external thing, right? We want to be able to decide the r based on some property of the sequence itself.
Okay.
I mean, we want to be able to decide that such an r exists without finding the r. Okay,
Okay.
so how do you do that? So you just look at the property of what these r's have, what this r to the power n's have. The crucial property is that r to the power n by r to the power n plus 1 is r that is less than 1. Yeah, it behaves like this, right? That's how the geometry progression behaves,
Is
right?
1 by R, right?
Uh, uh, um, oh yeah, no. So I meant r to the power n, the an plus 1 by an
Okay.
is r is less than 1, right?
Yeah.
So this is the property that this geometric series has. Okay, so what we will
Okay.
do is we will just check if our series also has the same property. Okay,
Okay.
so we will check, so we will just try to mirror the thing and internalize the thing. Okay,
Okay.
so means not comparing it with, not exactly finding an r, but if there is some r, then 1 second, yeah. So if there is some r, then this will happen. So we just want to compute this ratio. Now if this ratio also comes out to be less than 1 in the limit,
Okay.
even in the limit, if in the limit it turns out to be strictly less than 1, okay, then also we can say that, yeah, then we can say that there is some r. You can
And if
say,
there is some R which is less than 1, it's
yeah,
definitely convergent.
yes, less than 1. But we have to prove this, okay? But right now we're just kind of making a guess. So we want to compare it with a very prototypical series, and we're not able to understand which r that is. So we just tend to mimic its properties in the internal
Okay.
series. Okay, and hopefully then that will get the answer, and we actually do end up getting it.
Okay.
So yeah, so let me see if I can. I mean, we can of course show it, but it's there. Yeah. Anyways, yeah. So this is basically then what the ratio test is. So we expect. So we expect. Okay, that limit an plus 1 by an and tends to infinity being less than 1 would imply that an summation an converges. Okay, because the same thing happens for the R series, for the geometric series.
Yeah.
Okay, and for this series, if there is such an R, then this series is also a very similar series. Okay, so we expect that the same thing would happen for this also, and we expect that if the same thing, if this happens, then it will also converge. Let's try to show it though. So,
Okay.
well, what is the very and certainly this is certainly one, even if without before showing it, certainly we understand that this is a much easier thing to do. Taking the ratio of the terms themselves without having to guess an external R is much easier, right?
Yeah.
So it's like we are, so it's like there was a, I mean, from a logical perspective, if you think about the structure of the sentence, then there exists quantifier in this, right? And usually
Yeah.
sentences in which there is a there exists and for all, those sentences are complicated, and we always try
Yeah.
to internalize it without, we always try to write the sentence in an equivalent way without using the there exists symbol. And this is like an
Yeah.
attempt to that. Like this happens throughout mathematics. So even if you see something like a solution to a quadratic equation, then there is this thing, there exists an x such that ax square plus bx plus c is equal to 0. There is always this
Yeah.
thing, right? But we always want to strive to remove this there exist and just answer it on the basis of a, b, and c, and that is the discriminant b square minus 4ac greater than equal to 0. These two are equivalent
Okay.
statements. This statement doesn't have a there exist. That's why we all love it.
Okay.
We all love
Okay.
to check the discriminant, right? We don't, if you
Yeah.
just decide, yeah. So this is also an attempt to that. So this is like a
Okay.
common pattern in mathematics. We always try to remove, this is a quantifier elimination, eliminating the quantifier. But anyways, that is probably not useful. Just yeah, lot of.
Okay.
So now let's try to show that if this happens, then it indeed converges.
So 1 minute. So if it's greater than one, can I say it diverges?
Yeah, the same proof. Once we prove it that it converges for less than 1, we'll be able to prove that it is bigger than 1, then it
Okay.
diverges. The problem will
Okay.
still be that what happens if it's equal to 1. Okay,
Okay.
so in that
Okay.
case,
Okay.
that's a problem, yeah. But let's first see less than 1 case. So the good thing about the real numbers is that there are a lot of them. So if the limit is less than 1, it means that the limit is something here, right? Let's say the limit, this limit, let's say it's L. L is less than 1, so the limit is L. Or maybe I can write it here like this, L, and there is 1, and this is, right? So if the limit is L and it's less than 1, it means that I can find a small neighborhood such that that neighborhood also is less than 1.
Okay.
I can just have a elbow room to move around, right? And that will
Okay.
all be less than 1. So this means, and since I picked an epsilon neighborhood, this means that this thing, this limit of this sequence, not an, this limit of the sequence of ratios, this
Yeah.
is bigger than L plus epsilon and less than L minus epsilon.
Okay.
Yeah, and which is less than 1, right? Not just less than 1, it's less than L plus epsilon. Yeah,
Yeah.
which means that it's less than something, which all of them are less than something which is less than 1.
Yeah.
That's more
Yeah.
than saying that all of them are just less than 1. Okay, yeah. So now yeah, now this is like, okay, so this happens for all n bigger than some n naught.
Okay.
Okay, so now see, I mean, now at this point there is this L plus this an, right? And you can continue this process, right? You can all like this an would be less than an minus 1, right? And there would be L plus epsilon multiplied with it, so we will get this. And you can continue
Okay.
doing this. You can continue doing this all the way along, and you can go till, I mean, you have to go till n naught because it doesn't happen after that. So
Yeah.
you will get some power, right? You will get some n minus n naught. Okay.
Yeah.
So now you see that the geometric series is starting to form. The geometry series that we were looking for initially is starting to form. So we have proved that an is less than L plus epsilon to the power n minus n naught an naught. Yeah, an naught is fixed,
Yeah.
and this we can do for all an bigger than that. So you sum it up. Basically, it's, we can forget about the an naught, that's a constant. We're basically summing up a series, a geometric series with ratio L plus epsilon. This L plus epsilon is the R, which was the mysterious R.
Okay. Okay.
Yeah, and so we are done, right? So it means that it does converge. Okay.
Okay.
Yeah.
Okay.
So yeah, and obviously in the same way, if it's bigger than one, in the same way you can prove that it doesn't work. Yeah? Means that it
Sir, one
diverges.
small thing. A
Mhm.
mod doesn't come here, like
The
somewhere.
mod actually
No.
does come in. Yeah, I didn't write it in the beginning, but we actually need a mod. Okay. So we will need actually not just this, but the mod to be less than one.
Yeah, sir,
Okay.
but one small doubt, sir.
Mhm.
Can the limit go inside the mod?
The limit, yeah, the limit, if it exists, it can go inside the mod because the mod is a continuous function.
So basically, I calculate the limit as usual and then take the absolute value.
Yeah. You can just do that.
Yeah.
Yes.
Okay.
Okay. So all that just works out, and mostly our series, the series that we are dealing with, are all going to be positive, right?
Okay. Okay.
So there is no question. So there is no problem with that. Um,
So what if
yes.
it's equal to one?
Yeah. Then it is inconclusive. We can't really say anything. Okay. So
Okay.
let me just give you an example. So for example, if you, so these ratio tests, as you can understand, will usually work for series which are something like, an x to the power n, right? I mean, which have
Okay.
something, and then there is a something to the power n, isn't
Okay.
it?
Okay.
This series is usually going to work for such things, maybe half to the
Okay.
power n, right? Because then only this ratio, as you can understand, is going to be less than one, because then the whole issue, the whole motivation has been to compare it with the geometric series. Okay, so it will work for these series, but it will not work for things like these, which converge very slowly, which converge slowly. Yeah. So for example, take series like the square series. The basically all these things repeat. So there is a 3 square and 4 square. It will not work for this. You can try. You can
Okay.
try. So we know that this converges. Yeah, we know that this series is converging.
Yeah.
But if you try to apply the ratio test on it, then what do you get?
You're gonna get limit n square by n plus one square.
Mm-hmm.
Yeah. So it will come exactly one, which is
Yeah,
inconclusive.
yeah, which we cannot say much about. We cannot say about from the geometrics from that.
Yeah.
Okay, so this basically means
Yeah.
that this series is changing very slowly, and it's
Okay.
dipping.
Yeah.
It's dipping, but the terms are dipping, but they're dipping too slowly for the ratio to be less than one.
Yeah.
Yeah,
Yeah.
so the ratio test is weak here. Okay, the
Yeah.
ratio test is basically useful. See, ratio test is nothing more powerful than it's not more powerful than comparison with a geometric series, because as we saw,
Okay.
whenever you can apply the ratio test, you can find a R. We even found the R, right? We found the L plus epsilon.
Yeah.
Yeah,
Yeah.
you can always find the R. So the ratio test is never going to be more powerful in theory than the limit comparison test with geometric series. Limit comparison test
Yeah.
with
Yeah.
geometry, it's not going to be more powerful than it. But computationally it is more powerful because it just is a matter of dividing two, because you don't have to think about finding the R.
Think of another series. Yeah.
Yeah,
Yeah.
exactly, that's the thing. But it will pass, it will be conclusive, it will be conclusive only in those cases where the limit comparison test would also have worked. Only that finding the R would have been a lot of work. Okay,
Okay.
so the ratio test is a computationally powerful tool, but theoretically it's not a more powerful tool than the limit comparison test with geometric series. Okay, however,
Okay.
these and we also saw how much was needed to prove this. We had to group, and we had to
Yeah.
do a very strange kind of grouping, right? So that was really something new, where a geometric series is just, you can even add it up, right?
Okay.
So
Okay.
that's where these series is converging is a much more powerful thing. Okay, but ratio test usually comes later because we see a lot of examples and then it comes, right?
Okay.
So
Okay.
that's a ratio test for you. That's it. Okay, and
Okay.
then
Okay.
maybe then we'll have to next class do the root test and so on. So I think, yeah, by next class we should be done. There is not much left.
Including that absolute convergence and all.
Hopefully, yes, because as you saw, the root test is such a small section. They have
Okay.
not,
Okay.
they do not have any problems on it. Maybe they have one problem. Yeah,
Okay.
they just have one problem on it. So the emphasis is probably not too much on these. Okay, so
Okay.
yeah, I mean, if
So basically, they just need you to know the test and not the proof and logic and all that.
not too, yeah, not too much, I think so. I don't, from the
Okay.
notes, that's what I can make out. Okay.
Okay.
Okay, but these
Okay.
tests interesting problems can be done based on these, but since that's not in the notes, so I'm not doing it. If you want, I can do it
Okay.
later, but you, I think your exam is on Wednesday, so you'll not have
Yeah.
time.
Yeah. Okay.
Okay, so that's it. So
Yeah. So tomorrow,
yes,
what's the time?
tomorrow seems to be difficult. So tomorrow I have to take a class at 1, so that's 1 hour. I have to spend 1.5 hours almost there. And just 1 second, and then I have to take another class. So tomorrow already 2 hours, and I usually I keep, like, I don't want to take more than 3 hours any day teaching. Okay,
Okay.
so I can take a 1 hour class tomorrow, but not more than that. Actually, I had a 2 hour class, another 2 hour class scheduled, but I canceled it because I don't want to take 4 hours class a day. Okay. So I can take a 1 hour class. I can take that in the night anytime. Actually, I can take it in the morning also, but only 1 hour. I cannot take more than 1 hour tomorrow. And
So
then
then on Monday.
yeah, so Monday again I can take one. So 1 hour tomorrow, 1 hour Monday we can complete if you want to
Okay.
do
Okay.
it
Yeah,
like that.
that'll be good.
That will be better for you
So
also
tomorrow,
and
what
better
time?
tomorrow. So tomorrow we can do uh tomorrow you're free almost all day, right?
Yeah.
Yeah,
Yeah.
yeah. So I'm also, it's only that if I have to go to play in the morning, that's not very sure. But yeah, but 12 o'clock should work. This same time will work. No, 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 no. Same time
One
will not work.
o'clock.
So no, 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 no. 1 o'clock will not work. Sorry. 11 will surely work. That because
Okay.
there
Yeah.
will cannot be
Yeah.
anything at that time. So 11 tomorrow,
Yeah.
1 hour only.
Yeah.
Okay. Yes.
Okay.
Good
Sure.
then.
Yeah.
Yeah.
Thank you.
Okay. Bye.